Today, let's look at how to find the solution for the support vector machine, the SVM. SVM is usually defined in very high dimensional space, sometimes infinite dimensional space. So a natural question here is that how can we find the solution to this problem? It turns out the answer is a dual formulation of the SVM that we don't actually need to directly optimize in the infinite dimension. We only need the inner products between data points. Okay, let's get started. So suppose we are given n data points, xi, yi. The xi is the input features lives in some d-dimensional space. Then the yi is the class labels that can either take -1 or +1. The common theme with SVM is that we would like to define a feature map that takes us from x, the input, to the feature space phi of x. This phi of x can be some nonlinear transformation of the original data points. It can either be explicit or implicit. In the common formulation of the SVM, we usually use the implicit feature map that lives in some infinite dimensional space. But the thing here is that for the SVM, it is a linear classifier in the feature space. This is an important point. So SVM is linear in the feature space in phi of x. But it can be nonlinear in the input space x. So that is the key. So last time we talked about the geometry of SVM. The idea is that we want to find the linear classifier that maximizes the margin between the two classes, where the margin can be defined as the distance from this decision boundary to the data points, to the two class data points, right? We want to maximize this margin as our best linear classification. And then here I should also emphasize that this decision boundary is linear, right? So that means decision boundary can be written as a linear function for this, right? As an input space, as a feature space, phi of x, right? So that is the form of decision boundary. This equals to 0. Okay, then last time we also formulated the optimization problem for the SVM. We started with the hinge laws and draw the parallel to the logistic regression to write down the optimization problem. Then we rewrite the problem into a constraint form. This is a version of the soft margin SVM. So we have this constraint form here that the first term we said that this has to do with the margin, right? When we minimize this weight, the norm of the weight, we are maximizing the margin. And then the second term here has to do with violations, right? So for the soft margin SVM, we have the second term, but for the hard margin SVM, we don't have the second term. So geometrically, what this means is that for the soft margin SVM, so we have these two. These two kind of forms a margin around the decision boundary, right? So we want our data points to lie beyond that. So hard SVM, right? So hard SVM cannot violate this boundary here, right? It means that all the points must lie beyond. But for the soft margin SVM, there could be cases where the points live inside this margin, right? Meaning that there can be red dots, live inside here, and then the blue dots also live inside here, right? So that is allowed for the soft margin SVM. Then for this video, our main goal today is to solve this problem. But you'll see the challenge here is that if phi of xi lives in some infinite dimensional space, then this W vector is also infinite dimension, right? So it means that it's essentially not it's not computable for this optimization problem, right? When the feature map is implicit. I should say here, if we know the feature map, if the feature map is explicit, we can actually solve this problem directly. But that is not the common case we use for SVM. So now we should think about how to solve this problem. So here, let me just say an intuition first, right? So the intuition is that SVM is a linear classifier in the feature space, right? In phi of x. So this implies that we can actually write down the classifier as write down the decision boundary as a linear combination for all the training data points, right? So it means that so this implies that our weight vector, the weight vector is actually a linear combination for all the training data because it lives in the same space, right? It means that W is equals to the linear combination of all the data points, right? I'm going to use a different subscript J here, right? So geometrically, this is our W vector, right? It is perpendicular to the decision boundary. So uh, so both so that is the key intuition here, right? And then when we just plug in this expression into the decision boundary f of x, so f of x equals to W transpose phi x plus b, and that equals to summation of j over j. Then we have phi xj transpose phi x plus b. So you see here, right? This is the key, right? Because when we plug this expression back in, we have this inner product, right? This is the inner product between phi xj and phi x, right? That turns out to be the kernel, right? So it's going to be xjx, right? This is where the kernel comes in. If we are considering the training data points, let's say that we are looking at one particular data I, right, the xi here, and then we can just replace this inner product with the data point xi, right? So this is exactly where the kernel matrix comes in. That is something we want to show using the dual formulation for this problem. We will derive that using algebra without making this assumption directly. But you'll see that this is really the intuition why this whole thing works. Okay, now let me start a new page and let's derive the dual formulation for the SVM. Okay, now let's consider how to solve this soft margin SVM. So first, let me just write out the parameters that we need. So the parameters are uh, are the W vector, the weight vector, the bias, and psi I. So these are the parameters we need to solve. So here we are solving the soft margin SVM, right? So that means we have this chi parameters. For hard margin SVM, we don't have those. So that would be a slightly easier problem to solve, but it's very similar to this one. So the first thing that we can do is to write out the Lagrangian. So the Lagrangian we just combine the optimized, the minimized term with the constraint using a multiplier. So that gives us the Lagrangian. So let's just define this as L. Then we have let me just write the parameters later. So we have the first term, the minimized term, I minus. Okay, so see that here the alpha I and mu I here are the multiplier. Right, these are the multiplier. So alpha I and mu I. So that means our Lagrangian has the parameters of W, B, then psi I, also alpha I, mu I, right? So there are 5 parameters for our Lagrangian here. So one thing I want to emphasize here is that this Lagrangian can give us a dual problem. So I should say that our problem, the problem here is the primal problem. Then after we write out the Lagrangian, we'll also have the dual problem. So the difference between the two is that we consider different parameters to be optimized with respect to. So for the primal problem, we are optimized with respect to W and B, right? With respect to W, B, and okay, and chi I, right? So these are the parameters. But for the dual problem, we want to optimize with respect to with respect to the multiplier parameters, right? It's going to be alpha I and mu I. That is the difference between the two problems. But these two problems are connected through the Lagrangian. And there's also another interesting interpretation to it that has to do with the KKT conditions for the SVM problem. We can actually interpret the support vectors using it. So I'll cover more details of that in the next video. For this particular video, we probably don't need it. Let us focus on how to solve this dual problem first. Okay, so once we write out the Lagrangian, we can also write out the stationary conditions for the Lagrangian. We just take the derivative of the L with respect to our parameters, right? We need to set this derivative with respect to W equals to 0, with respect to B equals to 0. And then also we want to set this with respect to psi I equals to 0, right? So this is called the stationary. Um, so this is a stationarity, which is part of the KKT conditions. So we have the first one equals to W minus this term is linear, I think. Yeah. So you have the alpha I yi phi alpha xi equals to 0. Then the second one that give us equals to 0. So the third one, I think, so first we have the C, right? And then second term here, I think, oh, here we also have psi I, right? So that's going to give us minus alpha I, and then minus mu I equals to 0. Oh, and for the Lagrangian, I forgot to say that alpha I and mu I need to be greater than 0, right? So this is important. It's also part of the KKT conditions, right? This is called the dual feasibility, I think. There are actually four conditions for the KKT, but they are unified under one geometrical picture. We're going to talk about that next time. Okay, so this is nice, right? We have three equations in the end. And let me just move the terms a little bit. So the first term is super neat, right? We have W equals to sum of we directly see it, right? The first term tells us it's a linear combination of our feature of our sorry of our training data. This is exactly our intuition, right? Because the weight vector lives in the same space as the training data, so it's just going to be a linear combination of that. This is perfect. Then the second one is that then we also have equals to 0, and then we also have alpha I equals to C minus mu I. Okay, this is great. So remember for our dual problem here, we consider alpha to be the parameters, alpha and mu to be the parameters instead of the W and B and chi, right? So this means that we can actually plug in this expression of W into the Lagrangian and then rewrite the problem with respect to alpha. So that's what we're going to do, right? We will basically change the parameter for this problem from W to alpha. This is this is the key idea for the dual formulation, right? So we're changing from W to alpha. W, we also have B and chi, right? So so that is the parameters we want to optimize in the dual formulation. Let me just start a new page and then basically plug in this W into the Lagrangian to see what's going on. Okay, now let's take a closer look at our Lagrangian and to think about how we can interpret the dual problem for this for the SVM, right? So a very nice way to think about it is that the Lagrangian is a panelized primal problem. So what I mean by that is that it's because those two terms, right? When we add the constraint into the problem, these two terms are both greater or equal to zero, right? This the reason being that the multiplier that we used in here is greater or equal to zero, the alpha and the mu, and then the constraint must be satisfied, right? So that means the next term, these two terms here also need to be greater or equal to zero. So this whole thing taken together is kind of like a panelized primal problem, right? So it's a penalty. And then it's also mean that L is kind of like the lower bound for the primal problem. Then to connect with the dual problem, we actually want to make the penalty as small as possible. So it turns out that a very neat fact in optimization is that the minimize the primal is actually equivalent to maximize the dual. So this is a key insight that we're going to see more of this next time. But for here, we can just accept this as a fact, right? So remember that our primal problem is with respect to the parameters W, B, and chi I, right? The dual problem is defined with respect to the multiplier terms, right? Alpha I and mu I, right? So we want to, so it's kind of this, you can think of this alpha and mu I kind of control the strength for the penalty. We want to make that as small as possible. And when the maximizer is reached, that is the same. That is the same as minimizing the primal problem. This is also known as a strong duality in optimization theory. Well, but for the purpose of this video, let's just accept this as a fact, saying that we can actually maximize the problem with respect to alpha, and that will help us to reach the solution for the SVM. So let's do that first. Okay, so now we can do is that we can just plug in those three equations back into the Lagrangian to see what happens, right? So let's just plug in everything. I'm not going to write the parameters. So we have the norm of the W vector. That's going to give us a half. Then alpha I, alpha j, yi, yj, phi xi, transpose phi xj. That's the first term. Then the second term, we have C times summation chi I. That doesn't change. I just leave it for now. Then the third term, we just plug in the vector W into it. Okay, this is going to be a long term. You have alpha I, yi, and then the summation alpha j, yj, phi xj, transpose phi xi. Then we also have the B term, right? Let me just write out each term separately. It's going to be minus, we'll have alpha I, yi, B plus summation of alpha I minus alpha I chi I minus mu I chi I, right? This is a very long expression, but now I think we can do quite a bit canceling in here, right? So so first for the last two terms, right, we can combine them together. That's gonna give us because alpha I plus mu I equals to C, right? We'll have summations. We'll have C times summation chi I, right, for the last term. Then what we can do, we can also combine these two terms, right? Combine these two terms together, that's gonna cancel a half, right? We're just gonna cancel the first term completely and then have a half in here. Okay, and what else can we do here? Okay, we can actually cancel out these two terms as well, right? These two will canceled. This would be a minus, right? We have a minus in here, right? And then also we have the alpha I and alpha I yi equals to 0, right? You have this condition here, that means this term also going to cancel to 0. So this equation can simplify quite a bit once we cancel everything. So we'll have summation I go from 1 to n alpha I minus a half alpha I. Let me just write out the double summation alpha I alpha j yi yj and then phi xi transpose phi xj. Okay, this is a very neat formula. So see here that all the term we left are the alphas, right? We don't even have the mu term left in it. And then to solve this problem, we can, let me just also write out the constraint for it, right? So we have the constraint of alpha I greater or equals to 0. And then because the mu I term here is greater or equal to 0, right? So that means our alpha I must be smaller or equal to C. Right, this is because mu I is greater or equal to 0, right? According to this equation here. So that is a constraint we have. And then we also have another constraint being the summation of alpha I yi equals to 0, right? We still need that. Okay, so this is the optimization problem we got in the end. Let me just copy it to the next page to just clean up a little bit so we can see everything clearly. Okay, so this is a dual problem for the SVM after cleanup. So we have something very nice in here. You'll see that we have the inner product between the phi xi and phi xj, right? So this is the inner product. We can define this as kij. Right, that means we completely get rid of the feature map if it's infinite dimension. All we care about is the inner product between the data points. So here we can actually also write out the matrix form. That's gonna be even nicer. Let's do that. So the matrix form will have the max with respect to alpha. Alpha now become a vector, right? We have the 1 transpose alpha minus a half alpha transpose y k y alpha. Or I should say that's k here, kij equals to the inner product between data points phi I and phi xj, right? And then y is a diagonal matrix, right? That has all the y values, y1 all the way to yn. So that is the matrix y, right? Then we also have the constraint. Right? We have the constraint as alpha greater or equal to 0, smaller or equal than C. We also have alpha transpose y equals to 0. Right? So this problem here is called quadratic programming. It can be solved very efficiently. So see this here that the constraint is important, right? Because without the constraints, if we just solve this optimization problem, that becomes almost trivial to solve, right? But once we have the constraint, we need to use quadratic programming and to solve this problem. And then one thing here is that so this K matrix is positive semi-definite. So that gives us a nice convex optimization problem. So that's why the optimal parameters for the SVM exist, right? This is because K matrix is positive semi-definite, it's PSD, right? And then sometimes we also write this whole thing here as Q, right? So this is equals to this is second term can be also written as alpha transpose Q alpha, right? So Q is also going to be positive semi-definite. So that's important for quadratic programming to have this solution, right? So here, so the reason of K being positive semi-definite is because it has all the inner products, right? So it have all the inner products. If everything is finite, you can think of it as phi transpose phi, right? That is the K matrix. If everything is finite, so this is a classical matrix. This is a classical positive semi-definite matrix. So that is required for our kernel matrix K here. Okay, so that's pretty much how we solve the support vector machine. Now, let me just bring everything together to make a comparison table between the primal problems and the dual problem for the SVM to summarize what we did. Okay, now let's do a side-by-side comparison between the primal and the dual problem for the SVM to make things clear. Okay, so the first thing we can consider is a parameter for the two problems, right? For the primal problem, we have the main parameter as W and B. Whereas in the dual problem, we have the parameter of alpha and B. Right, so the P parameters here is the intercept, but we don't need to worry about that too much. So the main difference here is that we are changing our parameters from W to alpha, right? So W have the same dimension as the number of features. So this become problematic once we are in infinite dimensional space, right? So that means our W vector here become infinite dimensional. We can solve it. But for alpha, there are only n number of alphas, right? So we have alpha 1 to alpha n. That's the same number as the number of data points, training data point for the SVM. Then the second thing we can write is a function we use for prediction, right? Let's do the in-sample prediction first. This is a prediction for the training data. We have f of xi equals to W transpose phi of xi plus b. So that's how we predict how we make the in-sample prediction. Then for the dual problem, we can actually write on the same equation, but plug in the W weight vector with our estimate using alpha, right? We can have the same. We can start with the same. Then we can plug this in with our estimate using the quadratic programming. Remember that we have this relationship of, let me just write it first. We have the W star equals to summation as a linear combination of the training data points, right? The alpha I star and then yi phi of xi, right? So this is the equation we're going to use to plug in for our weight vector W. So here we'll have, let me just change the subscript to J, and then we'll have summation of J goes from 1 to N, then alpha J star Yi, and then, sorry, Yj, and then phi xj transpose phi xi plus B. It means that we can replace this with a kernel, right? We can replace this with a um, alpha j star yj and then kij plus b. So that's going to be our predicted value in sample prediction. Then for the out of sample prediction, it's going to be very similar. So we just basically replace this xi with x, right? That's going to be the same. It's going to be very similar to the equation we write down. Right, so we have f of x equals to w transpose phi x plus b. So here we'll have fx equals to summation j goes from 1 to n alpha j star yj k x xj plus b. Okay, so all of this means that this implies that our decision boundary, so it implies our decision boundary can also be written down in this kernel form, right? So decision boundary is just it's just gonna be this, right? It's gonna be w transpose phi x plus b equals to 0, right? In here we also have the kernel form of the same thing. Alpha j star yj k x xj plus b equals to 0. All of this is actually the result of our weight vector lives in the span of the training data points, right? So that's the key intuition. And then, using the dual derivation here, we convert this whole problem into a problem of quadratic programming from which we can solve for the parameters alpha j star. And then we can obtain the prediction as a sum of a bunch of kernel functions, as well as the decision boundary also as a sum of a bunch of kernel functions. So the thing here is that in practice, when we apply in SVM, all we need to do is to specify the kernel function k between the data points. We only need the inner product between the data points in their feature map without even explicitly saying what is a feature map, right? So all we need is a k function here. And then, the k function is nonlinear, right? So that means our decision boundary here is also going to be nonlinear in the input space of x. Okay, so that's pretty much about this video. And for the next video, we're going to look at the KKT conditions applied in the SVM. That will help us to tighten up the connection between the primal problem and the dual problem from an optimization view. Also, using the KKT condition, we can interpret the support vectors a little better. So it turns out that the alpha j here is very sparse. So this is sparse. It only has non-zero values in the support vectors. So that can be revealed using the KKT conditions. It's something we're going to look at next time.